extensions of K, so they're field extensions, where certain Cauchy sequences that don't necessarily converge in K converge in K. So the standard example is the completion of the rational numbers given by the real numbers. If you take Cauchy sequences for the usual absolute value on Q, and you join the limits of all the Cauchy sequences, you get the real numbers. So we're going to do that more generally. And we're going to complete a field with respect to evaluation. So evaluation on K, or on K star, is just going to be a homomorphism to the positive real numbers. So we're going to assume that we know this completion. In all the theories of completions, you sort of give yourself the real numbers. You're allowed to use that. So evaluation is going to be a homomorphism from the multiplicative group of the field to the multiplicative group of positive real numbers. So a homomorphism means, of course, that the valuation of the product is the product of evaluations, right? That's what it means to be a homomorphism. But it also has to have something to do with addition. And the condition on addition is that the absolute value of the sum should be less than or equal to the sum of the absolute values. Namely, you should have a triangle wall. And if you have a homomorphism that satisfies this property, you call it evaluation. Okay, so what are valuations on number fields? Well, you have the valuations like the absolute value at Q, which occur at infinity. So if we take K tensor R, we saw as an R algebra, that looks like R1 copies of R and R2 copies of the complex numbers, depending on how many roots of the fundamental polynomial generating K are real and complex. Okay, so that means that we can embed, so we have R1 different embeddings, okay, into the real numbers, and we have R2 embeddings up to conjugation, because once you have one embedding, you can always conjugate it, of K into the complex numbers. So if we can do valuations on the real and complex numbers, we can get them on K. And on the real numbers, you have the usual absolute value. So that gives a map from K star, each real root, real place, gives a map from K star to R star, and then on that we can take the homomorphism, which is the usual absolute value, R star plus, where the absolute value of X is plus or minus X, depending on whether X is positive or negative, and that satisfies the triangle law. That's a nice property of the absolute value. And for each complex place, we have an embedding of K into the complex numbers, well defined up to conjugation. So if we choose the absolute value on the complex numbers, that will give a valuation on K. But we don't do that. It turns out more convenient, and you're going to see for a moment, to take the absolute value squared. So that's Z times Z bar. And of course that doesn't depend on, you can conjugate here and you still get the same valuation on K star. And the absolute value squared satisfies the triangle law just like the absolute value does. So that gives us R1 plus R2 valuations on our number field. And they're called the Archimedean valuations. I'll say why. Of course, Archimedes didn't study these valuations. And they're R1 plus R2 of them. Now, why did I take the square in the complex case? Because they have the following nice property. So I'll call those the valuations V dividing infinity. The valuations at infinity. So because if you take the product for any alpha in K star, if you take the product over all these valuations, V dividing infinity, of that valuation of alpha, okay, then I claim that that's equal to the absolute value of the norm of alpha, where this is an element in Q star given by the norm, and then you take the usual real absolute value of that. And the reason is that this is just equal to the product over all homomorphisms, sigma from K into C, and there are n homomorphisms in in homomorphisms, where n is the degree, of the absolute value, complex absolute value of sigma of alpha. Because for a real place, it's just the absolute value, and for a complex place, you get it once for sigma and once for sigma bar, and so you get z times z bar. And if you think about this, this is the absolute value of the product of the sigma of alphas, and the product of the sigma of alphas is the norm of alpha, the different roots of the polynomial. And so if you take all of these R1 plus R2, this is the product of R1 plus R2 terms, you get this formula. And that's the reason why we take the square of the complex absolute value at a complex place. Okay, now beyond these valuations, there are valuations for each prime ideal in the ring of integers. And then we'll see where Archimedes comes in. So, if P is an ideal, prime ideal, then for every alpha in K star, we get an integer, which is the p-adic ordinal of alpha, which is it's the power of P dividing an ideal. Namely, you take the prime factorization of the fractional ideal alpha times A, product of Pi to the Mi, and almost all of the primes don't divide alpha, so almost all these exponents are zero, and if it's non-zero, you call that the P ordinal of alpha. Now that is additive. If you multiply alpha times beta, you get ord P alpha plus ord P beta, because you just multiply the two ideals and their exponents add. And it has the nice property that if you take the sum of two things, and you want to see what prime divides it, then let me actually get this right so I don't do it wrong. It's greater than or equal to the minimum of the two. Because if some power of suppose alpha is divisible by a left power of P than beta, then the power of P dividing their sum is exactly the power of P dividing alpha. So that's the minimum. When could it be? So it's equal if they're different. It's equal if different. On the other hand, if two things are both divisible by P, it's certainly possible that their sum is divisible by P squared. So it's greater than or equal to the minimum. All right, that's not evaluation because first of all, this would be a map to the additive group. But if we wanted to make it evaluation, we could take any constant and define the valuation of alpha at P to be C to the minus ord P of alpha. Then that has the property that, first of all, that this is true by this law, and then that the evaluation of alpha plus beta at P is less than or equal to the maximum of the valuation of alpha at P. So value of beta. That follows from this law. And that's certainly less than or equal to the sum of the two valuations. So it satisfies the triangle law in a very powerful form. All right, now notice that if you do this definition and you take the valuation of any integer is less than or equal to 1. All integers. Because the p-adic ordinal of any integer is non-negative, right? So this would be less than or equal to 1. Okay, and that implies that if I multiply alpha by any integer, the valuation of that is less than or equal to the valuation of alpha. Okay? Now notice how different that is in the real case. So Archimedes realized when he was doing his work on geometry that Euclid had omitted an axiom about lengths. Euclid was, of course, working with real lengths. And the Archimedean axiom that he needed Archimedean axiom, which he put in his work, is for any two lengths x and y, there exists an integer n such that nx is bigger than y. I mean, you had to compare lengths in Euclid. And Euclid was constantly, for example, proving things about triangles with irrational sides by chopping them up and saying, well, if you take enough multiples of this, you get this side, and enough multiples of this, you get this side. But you needed to be able to, no matter how small a length, you need to be able to multiply it by something to get bigger than the second length. Okay, that's false over here. Because no matter what I multiply, no matter what I have as to x, if I multiply it by an integer, it doesn't get any bigger. So it doesn't get bigger than y. So consequently, these valuations are called non-Archimedean. They don't satisfy that axiom. And consequently, these valuations, for reasons of sort of default, are called Archimedean. Okay. So it turns out, and we're going to see why in a second, that there's a best choice for this constant. And the best choice for this constant is the number of elements in the residue field. So we take C, and you'll see Y. So that's a power of P, right? Sometimes called P. So norm of P to the minus or P alpha. That turns out to be the right constant to take to get it. That's called the normalized p-adic valuation. So remember, norm of P is this is the size, is the index of P in the ring of integers. Why is that the right choice? Well, let's compute. Okay, let's take this one. Suppose we take a given alpha and k star. This was a finite product, but suppose we try to compute the product over all p of the norm of alpha of p. Now, you might say that's impossible, it's an infinite product, but in fact, almost all terms in this product are 1. Because for a given value alpha, almost all these exponents are 0. So since almost all the terms are 1, this really reduces to a finite product over the primes occurring in the factorization of the ideal A alpha. Okay, and what does that product come out to be? Well, it's equal to the product over P of norm of P to the minus or P of alpha, by definition, which is just 1 over the absolute value of the norm of alpha. Because if you write the ideal alpha A as the product of pi or pi of alpha, and you take the norms of both sides, on one side you get the inverse of this, and on the other side you get the norm of this ideal, which is the norm of alpha. Well, the absolute value of the norm of alpha. Well, that's interesting because this product perfectly cancels this product. And so if you put them together, you get the product formula, which is the key thing, as Artin realized, for the valuations, which says that if we have an element in K star, and you take the product over all the valuations of alpha v, again, it looks like an infinite product, but almost all terms are 1. You get a finite number of contributions for primes, you get another finite number of contributions in infinity, and that's equal to 1. So for example, if I were doing this for the rational numbers, just to give you an idea, and I took the rational number 3/2, and I took the product over all v of 3/2, what would I get? Well, I'd get 3/2 at infinity times, well, it has valuation -1 at 2, so 2 to the first power, then it has valuation 1 at 3 times 3 to the -1 power, and that would be 1. Okay? So we'll come back to the product formula, which is the key thing when we do the EDELs in a little bit. Okay, so now I have to talk to you about how you make a completion for each valuation. And as I say, this is a bit of a cheat because I'm going to assume that we've already understood how to make the real numbers. The foundations of all analysis courses start with the construction of the real numbers. And there are tricks in that case that you can use because you have a notion of positivity and greater than, and all that kind of stuff, which is what Dedekind used to define real numbers by Dedekind cuts. Okay, so what is a completion? A completion is going to be completion of K with respect to some fixed valuation B. So it's going to be it's going to be a field KV containing K where all Cauchy sequences in this valuation in K converge. Where Cauchy sequences alpha n of alpha in K star, or alpha in K, converge. And converge means, well, Cauchy sequence means that for all epsilon greater than 0, there exists an n such that if n and m are greater than n, the valuation of alpha n minus alpha m is less than epsilon. Remember, this is now a real number, which is less than epsilon. And converge means there's an actual alpha in KV such that this limit, which is the limit of the sequence. Okay, and we're going to prove to evaluation V extends to KV star. So it gives evaluation a homomorphism on the completion, not just on the field. And K is dense in KV using the metric topology. We're going to given by this valuation. So once we have a valuation extended, this can be viewed as a metric space, and K is a subset of it, and it turns out to be a dense subset. And this completion is unique up to a continuous homomorphism. For example, the complex numbers are the completion of the Gaussian numbers at infinity, and that's unique up to complex conjugation. Okay, so how do you do this? So it's very clever of idea of Artin's that you define this completion as the quotient of a ring by a maximal ideal. And the ring you take R as the ring of all Cauchy sequences of alpha n from K. So you have to know that if you add two Cauchy sequences, you get a Cauchy sequence, and if you multiply two Cauchy sequences, you get a Cauchy sequence, and you have a Cauchy sequence 1, 1, 1, 1, 1, 1, which is the identity, etc. And then you have an ideal of all null sequences, namely sequences that converge to 0. So 0 is in K, so you can talk about when a sequence converges to 0, and that gives an ideal because if you add two sequences converging to 0, it converges to 0. If you multiply a sequence converging to 0 by any fixed element in this ring, you still get a Cauchy sequence that converges to 0. And then KV is defined as the quotient. And you have to prove that this is a maximal ideal. And it contains K because K embeds as the Cauchy sequence, alpha in K, embeds as the Cauchy sequence alpha, 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 alpha. So that's the embedding of K. And the extension of the valuation is, again, is a kind of a cheat. You define the new valuation of a Cauchy sequence, and you have to check that this only depends on the Cauchy sequence modulo the ideal of null sequences. This is defined as the limit in the real numbers of the absolute value of alpha n. And this turns out to be a Cauchy sequence of real numbers. And in the real numbers, we know it's complete by some other thing. So Cauchy sequences converge. So that defines the valuation of the sequence. And well, it's dense because if you have a Cauchy sequence, alpha n, that's the limit of, as n goes to infinity, of, let's call this I of alpha, of I of alpha n. So this is a constant sequence, alpha n all the way, and as you let n go to infinity, that converges to this Cauchy sequence. So that's the denseness of it. And well, I'll leave this part. This is a little bit harder, the unique up to continuous homomorphism. And you also have to prove, but it's actually a little harder, and you need the diagonal process. Think about this. To show KB is complete. Namely, we've only defined it to contain the limits of Cauchy sequences of alpha n and k. But now you have to take a Cauchy sequence of things which are in kV under this valuation and show that that converges to another Cauchy sequence. So to show k, so you must show, anyhow, that's a good exercise in metric spaces. Sequences of elements in kV converge to an element in kV. Okay, so this gives a way of taking a field with evaluation, producing a larger field. And if you do this for the rational numbers and the valuation from a prime p, then the completion is called the p-adic numbers. And if you do it for a number field and a prime p, you get an extension of the p-adic numbers. If you take k, and you take a prime p that divides the rational prime p, then this completion of k at p is a finite extension, it turns out, of qp. Okay. Now, let's take a look at the case v is equal to p, because it has things that are completely different than the case of the reals and the complex numbers. And it's related to the fact that the integers have valuation less than or equal to 1. So now assume b is associated to a prime p. Because of the non-Archimedean nature of things, if you take the alpha in Kp such that the absolute value of alpha at p is less than or equal to 1, and call that the ace at p. So that's like the that's like the interval for -1 to 1 in the real numbers, or the things inside the unit circle in the complex numbers. Okay? So what's unusual is that this is a subring. Of Kp. With the unit group, Kp star, the things which are in the ring and are invertible in the ring, are the alpha such that the alpha p is equal to 1. So the unit circle becomes the unit group in here. That's a much bigger thing. Robert Coleman used to like to call it the unit tire. Unit tire. Why is it a subring? Well, it's clearly closed under multiplication. That's not the problem, but it's also closed under addition, because the absolute value of alpha plus beta is less than or equal to the maximum, and the maximum is 1. So that's what goes wrong. If you add two real numbers of absolute value less than 1, you don't get a real number of absolute value less than 1. All right, and if you call this thing capital P, well, I'll distinguish it. Maybe I'll call it PV or something like that. Maybe I'll call this a V. So we think of it inside the completion. If you take PV to be the alpha such that the absolute value is less than 1, strictly less than 1, that's an ideal of AV, because if I multiply it by anything of absolute value less than or equal to 1, I'm still less than 1. An ideal. And it has to be the unique maximal ideal, because it's equal to AV minus the unit group. I mean, anything invertible in here has to have absolute value equal to 1, because the absolute value of the inverse is the inverse of the absolute value. And if you have a ring where I mean, this is sort of the largest thing that could be a non-trivial ideal, because if you had a unit, you get the full ring. So it's a local ring. And we're going to show it's a discrete valuation ring, and that its residue field is the same as the original residue field of A. So this is what gives the p-adic completion so much extra structure, that inside of the p-adic completion, which is a field, you have a natural ring. Notice that this contains the ring of integers, because the ring of integers are integral at all valuations, so that the valuation is less than or equal to 1 at all primes p. And okay. So we're going to prove the following. Proposition A, B is a discrete valuation ring with principal maximal ideal P V. The principal means it's of the form pi V A V for some element pi A V in A V. And this pi V is frequently called the uniformizing parameter. Okay, so the first thing I want to note is that the value group of KV star is exactly the same as the value group of K. That's the values of the valuation. And it's equal to q to the z, all powers of this q in R star plus. That looks like it looks pretty dense at 0, but that's a discrete subgroup. Because if you apply the logarithm map to get an isomorphism with R under plus, then the image of this is just integer multiples of log q. Okay, why is the valuation the same? See, that doesn't happen at the Archimedean places. It's certainly not the case that this is not equal to the value of the q. These are positive rational numbers. These are positive real numbers. But in the non-Archimedean case, you don't get any more values than the original values. And the reason is that alpha minus beta, if that's actually less than alpha, that means that the value of beta is equal to the value of alpha. It's the same thing for OR p's. So if the difference is smaller, so a higher power of p divides it, then the same power of p has to divide alpha and beta. Okay, now just imagine you had a Cauchy sequence, and so these are becoming arbitrarily small, so they're certainly smaller in absolute value than any one of the terms. So that means that the valuations on a Cauchy sequence become constant. So it says that so if alpha n is Cauchy, then the reason this sequence converges is because the terms are all constant from a certain point on, right? And so therefore, they're given by the usual valuation of some element in K star, because these are all elements in K star as constant, eventually constant. So you don't get any new valuations by taking the limit of valuations of Cauchy sequences. Okay, now, we're still trying to prove this. Let pi be an element in A with, in AV with with ORD P of pi equal to 1. There are certainly such elements. I mean, the valuation here takes value 1 over Q, so there's an element in KV star of valuation 1 over Q, and that lies in AV because its valuation is less than 1. Or you could say, look, if all I'm doing is finding an element in A that has just 1 power of the prime dividing it. Now you might not be able to write that element, that the ideal P may not be principal, but by multiplying it by other ideals which are in the inverse class, you can make a principal ideal which has only 1 power of P dividing it. So you could even choose this pi in A if you wanted to. But by this little argument, you could certainly choose it in AV. Okay, so that means that's the same thing as saying the valuation of pi is 1 over Q. It's strictly less than 1, but it's the largest it can be to be less than 1. So let's let I be any ideal, non-zero ideal in AV. Okay, and let Q to the minus n be equal to the maximum of the valuations of things which are in I. So valuations are less than or equal to 1 if you have an ideal, and they're all powers of Q, and just take the one that's the maximum. All right, then I claim, and that's what we're going to prove, that I is equal to alpha, which achieves the maximum valuation. I mean, these are valuations which are going down to 0 perhaps, and you take one that achieves the maximum value times A, and it's the same thing as pi to the n times A. So that'll show that any ideal in this ring has the form a power of pi, where pi is a uniformizing parameter times A. Okay? Let's see why that's true. Okay, well, I certainly contains alpha max times A, because alpha max is an element in I that maximizes these real numbers. So we have to prove the other direction. So, but for the other direction, suppose we have some element beta which is in I. Okay, well then the absolute value of beta is less than or equal to the absolute value of alpha max, right? Because this thing maximizes the valuations of elements on I, which says that the absolute value of beta over alpha is less than or equal to 1, right? Which says that beta over alpha max is an element in A, which says that beta is an element of alpha max times A. So anything in I is contained in here. And to see that it's equal to pi to the n, well, the reason that this ideal is equal to this ideal is that alpha max divided by pi to the n is in A star, because it has absolute value 1. So it's a unit. So they generate the same ideal. So that's the discrete valuation rate. The prime ideal is just 1 power of pi, and all the other ideals, p to the n, are pi to the n a. And you get integral ideals if n is greater than or equal to 1, n greater than or equal to 0, and you can take negative n and get fractional ideals in k if you like that sort of thing. All right. finally, we're going to prove, since we had A as a subring of this, we're going to prove that it's dense as a subring. Let's put that up here. Next proposition. And we'll identify the residue fields. And that'll give us a good picture of what AV looks like. 1, A is dense in AV, just like K was dense in KV. That's not completely obvious, as we're going to see. And the map from A to AV to AV mod pi to the n AV, this is the quotient map, is surjective. And gives an isomorphism. Isomorphism, I'll just take this out, A mod P to the n to AV mod pi to the n AV. And so all of these rings are there. This is a finite ring because A mod P was finite, right? And so the index of P to the n in A is the norm of P to the n. So that shows that these quotient rings are all finite. And in particular, final claim is that AV is the projective limit of AV mod pi to the n AV, which is the same as the projective limit of A mod P to the n of these finite rings. Because, well, you could construct out of a term here in the projective limit, which is something mod P, and then something mod P squared that reduces to it mod P, and then something mod P cubed that reduces to it mod P squared. You could construct a Cauchy sequence, and that Cauchy sequence has to converge in K, and it actually converges to an element in AV. And so that shows that this discrete valuation ring is a projective limit of finite rings. These are Artinian finite rings. And so in particular, it's a profinite ring. That just means the projective limit of finite rings. Okay, let's see how we do this. And then I think after this, we're ready to do the EDALs finally. Okay, as I say, this denseness is not completely obvious. We start proof, let X be an element in AV. We want to find some alpha in A that's close to it. Well, we know there exists alpha and beta in A such that X minus alpha over beta B is less than epsilon for any epsilon, because this is an element in K, and K is dense in KV. Okay, but how do we know we can do an element in A? Well, but the absolute value of X is less than 1. So, since this is very small, it has to have the same absolute value as this, so the absolute value of alpha over beta has to be equal to the absolute value of X, so that's less than or equal to 1, which means that alpha is in the ideal P to the ORD P of beta. Right? Okay. So we want to try to find some gamma. We want to find some gamma in A such that the absolute value of gamma minus alpha over beta is small. And then the absolute value, then gamma will be our close approximation to X. Okay, so what does this mean? Well, that means that multiplied through alpha minus beta gamma, we want to find a gamma so that that's less than the norm of beta times epsilon, so a very small number, or equivalently, that alpha is congruent to beta gamma mod with P to the capital N for large N. Can we solve that for a gamma in A? Well, what does that mean? Alpha, on the other hand, we know is in this ideal. But alpha is equal to A times beta plus P to the N for large N, because this ideal is exactly the ideal of things where the ORP P where alpha is in P to the ORP P of beta. See, this is divisible by P to the ORP P of beta, and then you don't get any worse than this. So that means you can make that, you then solve for gamma, and gamma gives you your close approximation. This is the ideal, I should have said. P to the ORP P of beta. Okay, well, the surjectivity follows from the fact that this ideal P to the N, this ideal PV in AV and PV to the N, is both open and closed. Open and closed. It's open because it's the things where the valuation of alpha is less than 1 over q to the n minus 1, and it's closed because it's the things where the valuation of alpha is less than or equal to 1 over q to the n. And so this preserves convergent sequences as it's closed. The complement of this is similarly closed. Well, that means that when you study this quotient, PV to the n, that it has, because you can put a topology on it, and it gets the discrete topology. I mean, you know, you're dividing out by an open subgroup. So this map is therefore surjective because this has the discrete topology, and this is dense. We just proved that. So it's dense in this quotient with the discrete topology, so the only way it can be dense in the discrete topology is to be onto. So that's the surjective homomorphism. The kernel is one of the things where the ORP P is greater than or equal to n, which is exactly this ideal. And so that gives this isomorphism of this ring with this ring, and from that, pretty much everything follows. But now, notice that since we've written this ring as a profinite ring, topologically, these things have the discrete topology, and so this gives us, so it's compact in the metric topology. Anything that's profinite is compact. And since this is an open subring of KV, that shows that the origin in KV has an open neighborhood whose closure is compact, so this shows that this field is locally compact, just like the real numbers in the metric topology. So the real numbers don't have a natural subgroup like this that you can use that is compact, but you can find open neighborhoods of the origin, say from -1 to 1, which have compact closure. Well, here you have an open compact subgroup of the thing, so it's locally compact. And that's the key thing we're going to need for these completions, that they're not just fields, but they're topological fields. It has a metric topology, and in that metric topology, it's locally compact. Now, we come to the brilliant idea of V-dells. I'm going to keep the product formula up, it's too good. And this idea was originally held by Chevalley as just an algebraic notion, but then people discovered that the real way to motivate it is topological. So we have our field embedded in all of its completions. And here we have K, and it's embedded in maybe KV is equal to R, and it might be embedded in some KP, which is QP or something. And what we'd like to do is put it in all of them. So that's the natural thing to do. Just take K and put it in the direct product over all valuations of KV. That makes sense, right? You just it's embedded in each one, so it's embedded in the direct product, and you just, alpha goes to its embedding in the V. Okay, and that looks like a great idea, except that there are infinitely many terms in this product, and so each one of these fields happens to be locally compact, but in the product topology, a product of locally compact spaces is not locally compact, in the same way that, R infinity is not a locally compact space. Okay, so you could say, well, I'll tell you what, instead of doing that, I'll put it in the direct sum, I'll take the direct sum over all V of KV. That is locally compact. This means the sequence is alpha V such that alpha V is equal to 0 for almost all V. That's what the direct sum is of fields. And that is locally compact because it's a union of finitely many. This is the union over S of product just the direct product of V and S of KV. We're over finite sets because you're only taking finitely many terms are non-zero. That's perfectly nice and locally compact. The problem is it doesn't contain the field, because an element in the field is non-zero in all of its completions. So it's not in the direct sum. So the idea is to choose something that's somewhere between the direct sum and the direct product that contains the field. And it would be nice if one could make that choice so that the something in between was actually itself locally compact in the product topology. And that's the idea of the adels. So the adels are going to be written like this. KB with respect to AB. So that's going to be a subring of the direct product. And it's going to contain the direct sum. But it also is going to contain the field embedded diagonally. And the idea is to take the elements in the direct product, which are in this subring at finite primes for almost all primes P. So these are equal to the sequences alpha V, such that alpha V is in AB for almost all but a finite number, all V. So that's clearly contained in the direct product where you make no restriction. It clearly contains the direct sum because if it's 0 in almost all places, it's certainly in the integers. Okay? But, and notice that I don't even have AV defined for all V, because at the Archimedean places you can't even say what you mean, but it's certainly defined for almost all V. And it contains the field K because if I have any alpha in K, it has only finitely many primes in its denominator. Any fixed alpha has only finitely many primes in its denominator. And so it embeds into this ring. And it's a ring because when you multiply two sequences like this, you get another thing like this, and add two. I mean, this is because this has the property of being a subring, it all works out nicely. Okay, now this can be written as a direct limit over S of things of the following form. You take the product of V and S of KV, where this is some finite set, finite and contains all the infinite primes, cross the product of V not in S, that's an infinite number of things, of AV. What's the union of these things? Because any adel, if you take the places where it's in the integers, is contained in something like this. And this is a locally compact set because this is a finite product of locally compact fields, which is locally compact, just like Rn is locally compact. And this is a product of compact groups, which by the Tikhonov theorem, no matter whether it's an infinite product or a finite product, is compact. And when you take the product of something locally compact by something compact, then the product topology is locally compact. So that gives the local compactness once you have all these facts about the localizations. the existence of the compact subring, et cetera, et cetera, et cetera. And finally, let's just define one homomorphism on the adels. Oh, and then I can tell you now what the edels are. So these are called the adels. They were not defined by Chevalley. Chevalley defined the edels, which are just the multiplicative group of this ring. And that turns out to be the restricted product of KV star with respect to the units, AV star. So again, you take the product of non-zero elements, so every edel is a collection of non-zero elements, almost all of which are units. And again, K star embeds as a subgroup of A star by taking diagonally embedded elements at each prime V. Okay, great. All right, here we go. So there are a lot of great theorems about this, but I'll give you, why did Chevalley call these things the edels? Well, let's consider the following. Suppose I took the subgroup of A star, let's call it, well, we have a subgroup, let's call it J, which is the product over V dividing infinity of KV star, cross the product over P of AP star. Okay, now that's a subgroup of the edels. I claim that the quotient group A star modulo J is isomorphic to the group of ideals. Okay. So in that sense, if you give yourself an edel, you're giving yourself more information than an ideal because you're giving yourself an ideal plus the information in here. Why? Well, because each KVP star by AP star is isomorphic to Z by taking an alpha here and taking it to the ORD P of alpha. And so, if I have an edel, I ignore the infinite components, so I'm dividing out by, I don't care what the infinite components, and I have all these finite components, and I take the modulo units, all I'm keeping track of is the power of P dividing that element. And the collection of powers of P, and this ideal, this group I, is the direct sum over primes of Z. And for each edel, only a finite number of components are not units, so you get an element in here. And then if I mod out by, if I take not only the quotient, but also J times K star, well, that turns out to be, well, if you take the image of K star in here, maps to the principal ideals. And so if I mod out by K star, this is isomorphic to the ideal class group. And the unit group is hiding too, because the unit group is exactly the intersection of those two. So somehow, inside of this miraculous object made out of the multiplicative groups of the completions, I have the unit group of the ring of integers, I have the ideal class group, I have all these structural things that I was dealing with, and it's all put together in this one marvelous package. Okay? And let's finish with this product formula, because the product formula has a great interpretation from the edelic point of view. Namely, I claim there's a homomorphism from the edels to the positive real numbers. A canonical homomorphism, which is called the edelic norm. And it's defined as follows. If I have an edel, I map it to the product over all V of the valuation of alpha at V. alpha V at V. And since almost all of these are units, almost all the terms in this product are 1, right? And it's a surjective map because on the real places and complex places, I can get any absolute value I want. So I get a surjective map to the positive real numbers, a homomorphism. And what the product formula says is that this subgroup is in the kernel of that map, right? Because if I apply this Delic norm to anything in K star, the product of all evaluations is 1. Okay, so we're going to prove a lot of topological theorems about the Adels and the Edels next week. So as on Thursday, we're going to aim for, first of all, that K embeds discretely and co-compact in the Adels. That's really the non-vanishing of the discriminant, as we're going to see. And then we're going to prove that K star embeds as a subgroup of the Edels, but not just the Edels. The Edels where the norm is equal to 1. That's the subgroup of, which is the kernel of this homomorphism, right? We saw this was in the kernel of the homomorphism. So we think of it as a subgroup of the kernel homomorphism that is discrete, and it's also co-compact there. And that turns out, you wouldn't be surprised to find out, to be both the finiteness of the class group and the finite generation of the unit group and the non-vanishing of the regulator. So all the basic theorems in algebraic number theory about class groups and discriminants and regulators are codified in these 2 wonderful statements. That the Adels contain the field as a discrete co-compact subgroup, and the Edels contain the multiplicative group. If you take the Edels of norm 1, then it's co-compact. If it isn't, if you don't take the Edels of norm 1, then you have a quotient which is not compact, and then the rest of the quotient is compact. So that's what we're going to pick up on Thursday. There are many, many, many good treatments of this in the literature. This would be a good topic for an undergraduate to make all these statements precise, etc. Get the do the topology properly. I'm sort of whisking through it today, but we'll do these discrete and co-compact statements next time, and then I'll show you how Tate reinterpreted Heckett's results. Instead of characters of this group IF mod PF, he studied characters from the Edels mod K star, the complex numbers, and showed that those were essentially the characters that were studied by Heckett. So this gives a framework for rethinking the classical results in 19th century number theory in an extremely flexible and coherent way. And in some sense, what people did realize was, instead of just thinking of the number field embedded in the real places and thinking of the ring of integers as a lattice there, you wanted to think of the number field embedded in all the places. You couldn't do the direct product, that was too large. You couldn't do the direct sum, that was too small. And this was just right. Good? Okay, see you next Thursday. Don't forget the other talks today.
Arizona with the student line.
Pardon?
Arizona with the student line.
Oh, yeah, I don't know. I always forget an announcement or two, so also the Arizona University.
We already have a bunch of people signed up.
Good.
It's
So don't be late.
Graduating them.